So I normally call this section extreme values and saddle points, but your book calls it maxima and minima problems. We are going to use partial derivatives to locate critical points for a function of two variables, not just one. Apply the second derivative test to identify a critical point as a local maximum, a local minimum, or a saddle point. And then examine critical points and boundary points to find absolute maximum and minimum values for a function of two variables. Now, I think this is kind of fun. Let's see what you think. All right, so we remember from, so let's, again, it always helps to go back to Calc 1. So let's go back to Calc 1. So we'll go take a trip back to Calc 1. Okay, so in Calc 1, if we had a function, all right, so here's f of x on an interval. So f of x looks like this. Okay, and so at this location, here A, here's B, here's C, here's D. So if we're looking at this interval, let's say, and we're going to cut it off. So let's say we chop it off right here. And then I'm going to chop it off right here. So I'm only looking at it on between those points. Okay, so between E, oh, let me make that dark, between E and F. Okay, so we have f of x on the interval EF. And we could say that f of x has local maximum at which points? At x equal to what? Anaya? Anaya?
Yes, what did you say? I'm sorry.
I said f of x has local maximum at the point, which points?
Oh, I can't see that. Is that a 3?
Where?
Oh, A and C.
Okay.
EA and EC.
No, at A, you are right.
Oh, I thought the
E and F are the endpoints.
Yeah, I just peeped that.
Okay. All right. So that it has local minimum at x equal to
B and D.
okay. So now where does it have an absolute max?
A. The absolute minimum is B.
Thank you. It's so refreshing to work with somebody who remembers their older courses. Yay. Okay, so let's go to 3D. So now we're back to Calc 3. Okay, so in Calculus 3, we need to generalize this theory to 3D. Okay, so the first thing is we're going to let M. So we're going to define M is equal to f of A, B. All right, this is the absolute max of f of x, y on a domain D or a domain R. And that's if m is bigger than or equal to f of x, y for all xy in my region R. And we're going to define little m to be f of CD is going to be the absolute min of f of x, y on the domain R if little m is less than or equal to all the f of x, y for all xy in my domain R. Okay? So
Yes.
I'm going to do a theorem. And my theorem says, let f of xy be a continuous function, all right, on the domain R. All right. And we're going to assume that R is contained in a simple curve in R2. Then F attains an absolute max and min on R. So what do I mean by that? So here's the base, and R may be, let's say R may look like this. So this is my region, my region that everything's floating over top of. Well, I can get that inside a simple closed curve. It's supposed to be simple. It's not supposed to cross over. Let's do that again. The whole region is enclosed in this curve. So therefore, the function has to contain a max and a min on there. Okay, let's define an interior point. Okay, so an interior point of R, okay, so XY is an interior point of R if there exists a disk about around XY that's contained solely in R, that's contained in R. Okay, and I'm going to define a boundary point, XY is a boundary point of R if every disk around XY contains both points in R and points not in R. Okay. So very simple. Okay, so I can draw my region to look like this. Okay, I pick a point. I can get a disk going around it that's contained solely in R. So that's an interior point. Okay. So I pick a point. I draw a disk around it. That's an interior point. I'll pick another point, draw a disk around it. Notice I have points in R and points that are not in R. So that's a boundary point. Is that clear?
Yes.
Okay. All right, so what we want to do is we're going to first look at, like we did before, local extreme values that are on the interior, and then we'll check the boundary. Okay. So to determine absolute max and min points, first, we're going to check interior points. If you remember, we called them critical points. And then we'll check boundary points. Just like we did before. Okay. So let's say we're on a disk in R. So this is a definition. Say we are on a disk in the region R. If f of AB is greater than or equal to f of x, y, for all xy in the disk. Oh, I gave the disk a name. I called it D. So let me call my disk D back here. Okay, then f of AB is a local max. And if f of AB is less than or equal to f of xy for all xy in D, then f of AB is a local min. Now, some of these things are easy, okay? Quick, fast, and dirty, easy. So let me give you an example. So here's some examples. So number one, we're going to consider the paraboloid, z is equal to x squared plus y squared. Okay, so remember this paraboloid in y, you got a paraboloid, and in x, you got a parabola. So this is the paraboloid. You remember it went around like that. And we can clearly see that right here is a minimum. Okay. Then we want to also consider the paraboloid z equal to 8 minus x squared minus y squared. And this was a paraboloid, started up here and came down like that. And it did the same thing in x. And if you remember, it also went like this. Okay. And so clearly right here is a max. All righty. So those are easy. No problem at all. Okay. So for the first one, if we look at y equals 0, which is the xz plane, in the xz plane, we're going to see something that looks like this. And you can see then that this is z is only a function of x. So the partial of z with respect to x is equal to 0. You have it's a minimum. And if I do the same picture for x equals 0, which is the YZ plane, we're going to see this picture. And so again, the partial of z with respect to x now is equal to 0. And again, we have a minimum. Okay, so that takes care of that one. But how about the one on the other side? Okay. I swear my phone's been ringing all day. Like, people are not going to be able to function if they don't contact me. And I don't need to talk to anybody. Okay. All right. So let's do this case. So in this case, I can do the same thing. All right. So if y is equal to 0, and I'm in the xz plane, I'm going to get something that looks like this. And again, the partial of z with respect to x is equal to 0 at that point, and I have a max. So you remember how when we, the derivative equals 0, you got a max or a min. But this way now, we have two ways to look at it. We can look at it the partial with respect to x and the partial with respect to y. So now, if x is equal to 0, so I'm in the yz plane. So now I'm going to get a similar picture. Okay. The partial of z is equal to 0. Z with respect to y is equal to 0. And again, I have a max. So life is good there. Okay. So we do have a theorem. Theorems are good. They help direct us to needed results. So it's the same as before. If f of xy has a local max or a local min at the point AB, and the partial of f with respect to x, so f sub x at AB and f sub y at AB both exist. Then the partials have to be 0. So f sub x at AB has to equal 0, has to equal f sub y at AB. Now remember, this is just like the theorem from before. Just because the partials equal 0 does not mean it has a max or a min there. This theorem says if it has a max or a min, then the partials have to be 0. So let's look at these two problems. So we had, go back to our examples. Okay, the first one, f of xy was x squared plus y squared. And we could clearly see that it had a min at the point 0, 0. So when you take the partial of f with respect to x, you get 2x, and then you take the partial of f with respect to y, you get 2y, okay? So if 2x, so if we let 2x equal 0 and we force 2y to equal 0, then we get that the point xy has to be the point 0, 0, which is exactly what we saw. Okay, and we had a local min. Okay. And the second one, where f of xy equaled 8 minus x squared minus y squared. We have the partial of f with respect to x is negative 2x, and the partial of f with respect to y is negative 2y. And if we force them to be 0, then we get that the point xy has to be 0, 0. And remember, we had a local max there. So yes, those satisfy the theorem that where we have a max, the partials are 0. Okay. So now life gets a little confusing. So now we want to look at case 3. So this is now going to be example 3. And now z equal to x squared minus y squared. Okay, so this is the case where this is the hyperbolic paraboloid. Okay, so if you remember the hyperbolic paraboloid, we get all kinds of things. Okay, so if z is equal to some c squared, which is positive, then you get c squared is equal to x squared minus y squared. And you get hyperbolus in this direction. Okay, so this is z is a constant. So this is for z equal to c squared as a constant. And then if z is equal to negative c squared, which is less than 0, then I get c squared is equal to y squared minus x squared. And now I'm going to get hyperbolas that face this direction. Okay. But if y is equal to a constant, then I get z is equal to c, whoa. That's wrong. Oh, because I switched these. So I did that wrong. These are backwards. Because I switched them. Yeah. Okay, let me just switch it back. This is supposed to be y squared minus x squared. And then this is supposed to be y squared minus x squared. And I was drawing them pictures. I said, something doesn't look right because here y can't be 0. Okay, good. And now I got this one right, y squared minus x squared. Nope, this one's wrong. This should be x squared minus y squared. And x can't be 0. Good. Okay, so now z is equal to c minus x squared. And so that's a parabola, an upside down parabola. Like that. This is z x. This is yx. And this is yx. Okay. And then if X is equal to a constant, you get Z is equal to Y squared minus C. And so therefore you get, wrong picture, wrong picture. You get a facing up parabola. Okay, so now this whole thing, if you remember, looks like this. I actually have a great picture in my notes. I hope I can do this. I have a really great picture in my notes. Okay, so I have a parabola here. And then I have a parabola down here. And then I have the hyperbola here. And then I have an hyperbola here. That's not too bad. So I get this hyperbolic paraboloid. And notice, even though the derivatives are 0 here, you can see the slope. The derivatives are 0 here. I don't have a max or a min. Okay, right there, I have a saddle. So there has to be more to this thing than just them being zeros. Because for this example, you have f of xy is y squared minus x squared. F sub x is negative 2x. F sub y is 2y. And if I set that equal to 0, I get the point 0, 0. But it's neither a max nor a min. In fact, it's a saddle point. So now we can see it's not enough to just say the partials are equal to 0. That f sub x is equal to f sub y. There's got to be more to it. Okay. All right. So here's a theorem. So there are 3 types. So they're the types of absolute extrema. Okay. So now we're going to assume that f of xy is continuous on R contained in a curve. So we're going to assume f of xy is continuous on a region R contained in some curve. And then we have f of AB, all right, is an absolute min absolute max or min if first thing has to happen. One, it's an interior point. And my phone rings again. Hang on 1 second. Yes. Hold on a minute. So it's an interior point where f sub x at AB equals 0 equals f sub y at AB. 2, it's an interior point where both the partials do not, where both the partials do not exist, where one of the partials may not exist. So it's an interior point where not both f sub x and f sub y exist. Okay, so those two things make it a critical point. So these two things are critical points. Or 3, it's a boundary point. Okay. All right, so what we're going to do is we're going to do what we did before. We're going to take derivatives, set them equal to 0, find our critical points. If they don't, if the function doesn't exist, the critical points don't exist there. Well, the derivatives don't exist there, or the derivatives are 0. We're going to check to see if that's a maximum or a min, and we must be on the domain. Okay. All right. So first thing we're going to do is we want to classify the critical points, then look to see if there's an extrema on the boundary, and then find out what's the biggest. Okay, so here's an example. All right, so this one is f of xy is equal to the square root of x squared plus y squared. Okay, so if you recall, this is also z. So if we recall, this is a cone. All right, so it's the top half of a cone. All right. Okay, so if I take f sub x, I get x over the square root of x squared plus y squared. And if I take f sub y, I get y over the square root of x squared plus y squared. All right, and so I can clearly see that f sub x and f sub y do not exist at the point 0, 0. So 0, 0 is a critical point. It's the only critical point. All right. Oh, I didn't give you a region R. I forgot. And R is the set of all x, y such that x squared plus y squared is 1. Okay, so this looks like and then down here, oh, that's too big. This is the region on the ground. Okay, so and actually it's a closed region. I'm including the bound. So that's the region on the ground. So this is R. All right. So inside R, that's the critical point. And F of 0, 0 is equal to 0. And this is our local min. It's actually an absolute min. And the entire boundary, every point, so the entire set, the set of all x, y, such that x squared plus y squared is equal to 1, that whole set is where we have a local max, F attains a local max. Okay, now let's do a real problem. Number 2, f of xy is equal to x cubed minus 3xy squared. So f sub x is 3x squared minus 3y squared. And f sub y is equal to negative 6xy. Okay. So I have x squared. So this, if I set this equal to 0, this gives me x squared minus y squared is equal to 0, where x, y is the 0.00. And then this, that state, that goes in there. So now I know f of 0, 0 is either a max or a min. Just from looking at this, or it could be something else, we're not sure. Okay. So if I look at a point bigger, let's say I let x get bigger. So say I look at f of h0, all right? That gives me h cubed. So this is negative if h is less than 0, and it's positive if h is greater than 0. So f of 0, 0 is not either a max or a min. It is a saddle. So there's got to be a better way for me to figure out what's a max or a min than just what we're doing. Okay? There's got to be some theorem to help me figure it out. So I have 4 minutes. I don't think I'm going to be able to finish this one. This is my favorite, one of my favorites. So find the absolute max and min of the function f of xy is equal to 3x squared plus xy on the region R. And R is the set of all xy such that y xy bounded by y is equal to x squared and y is equal to 4. Okay, so here's the region in the xy plane. So I have y is equal to x squared and y is equal to 4. So this is my region down here. And on top of that, there's a function floating over it, and I'm trying to maximize or minimize the function. So on the, here it is on the XY plane. This is my region on the ground. And then there's some function floating over top that I'm trying to maximize. So this is f of xy floating over top, z, which is 3x squared plus xy. And so what do? We start with f sub x. So f sub x is 6x plus y. And then f sub y is equal to x. So I need 6x plus y to equal 0 and x to equal 0. Well, if x is 0, y is 0, so this gives me the only critical point, 0, 0. So now I have my critical point 0, 0. What I now need to do is check the function on the boundary. Okay, and we'll pick up here tomorrow.